let's see. I have only like 1 minute left. Wonder if that's enough time to talk about electric power. Let me see if this formula makes sense to everyone. So this is the formula for electric power. So I guess I definitely don't have any time to do examples. But so let's say electric power. I would claim that the formula for power output by a battery, for example, would be that power due to a battery is equal to current times voltage. Can someone make sense of why this formula should be true?
Well, is that potential of a battery?
Yeah, this would be the potential of the battery. Potential energy or voltage being provided by the battery. Like, why would you expect this to be correct formula? So it comes down to remembering how all these quantities are defined. How is power defined? We may not have covered the power in Physics 4a. I kind of skip it in Physics 4a all the time. Anyone here remember the definition of power in physics? It relates to energy. Energy per what? That's the unit of energy, yeah? Per time, yeah. So power is rate of change of energy. This is the rate of change of energy. So if you're talking about units, energy is given in units of joule. Power is given in units of watt. And so watt is unit of power. And joules per second is 1 watt. So, okay, then what we need to justify here is that somehow this is giving you the rate of change of energy of battery. And since I'm already out of time, let me just go through this quickly. The way you see it is you write out what the current is. So current was defined as number of charges that flows through a point. Let's say number of charges that's leaving the positive terminal. That would be number of charges divided by the duration of time. So combining this back with the voltage of the battery, let me write out voltage of battery here. What does this expression here represent? Number of charge leaving the positive terminal of the battery multiplied by voltage of the battery. So you are looking at battery that looks like this. Positive terminal, negative. And you don't know what's happening here. Some sort of black box stuff happens here. But what you do know is that in time delta t, some amount of charge delta q is leaving the positive terminal. What else can you say? Can I say that the equal number of charges enter into the negative terminal of the battery in the same time? Right? Current here is the same current here. So in the same amount of time delta t, some charges are leaving the voltage of V battery. Some charges are entering the voltage of 0. What does that tell you about change of energy here? Same as what?
Constant, it doesn't change over time.
No, energy is not constant here. Amount of charge is the same because some charge left, some charge came in. But charge that left is not the same charge as charge that came in. Charges that are leaving, they are leaving at this electric potential. Charges that are entering at 0 electric potential. Which one has more potential energy? Ones that are leaving, right? So this represents the amount of energy that's being carried away by this many charges. Charge times voltage gives you a potential energy. And the charge that's coming in is not giving you any potential energy. So this is the amount of energy that's being lost each time interval with the charges that are leaving the battery. So that's the rate of change of energy divided by time. Rate of change of energy divided by time. So this is the basic formula for electric power. So we have 2 more days. 2 more? No, we have only 1 day assigned for more circuit problems. So we'll do a few more circuit problems on Monday, and we'll look at some implications of this formula, as in energy dissipated in the register and those things.